Okay, thank you very much, Rachel, and welcome everyone. Thanks a lot for coming along to listen to me ramble about fractals on a Saturday morning. So I'm not sure exactly how many people we have, 34 apparently, so that's good. I want to get a little bit of interaction in this session. So normally when I've given talks, similar to this before, I've been in a real lecture theatre, and there it's much easier to get interaction because I can sort of walk around the room and point at people, but it's going to be a little bit difficult for me to do that today. But I really hope we can use the chat function. So several times throughout the talk, I'm going to ask for opinions or suggestions, and if people can put their answers in the chat, then that would be great. And my idea is that lots of people answer the questions, and then I can just look and see all the answers as they come in, and then I can pick the ones I want. So hopefully, like, everybody contributes, and there's like 34 different answers to every question. So that would be my dream. And don't worry about putting anything silly in the chat, because everything I say is going to be sort of somewhat silly anyway. So if anyone's going to embarrass themselves, it's going to be me. So okay, so I'm going to talk to you about some mathematics, which is very close to my heart. I'm a pure mathematician. My day job usually comprises either teaching undergraduates mathematics or working on research. And most of my research is actually directly involved with fractals and the pure mathematics of fractals. And so what I want to do today is just to sort of tell you what a fractal is, if you haven't heard about it before, show you a few fun pictures, and convince you that fractals are interesting and in fact all around us throughout science and nature, as the title of the talk suggests. So I'm going to, so hopefully we're all on the same page, so let's get started. So I'm just going to show some pictures. I mean, every fractal seminar or talk should, of course, have lots of pictures in it, but this is maybe not quite the picture you expected to see. So just to see if this chat idea is going to work, can I ask my first question? So here's a picture. What is this? Does anyone know what this object is? So I've got the first chat. So someone said food, someone said broccoli, messed up cauliflower, vegetable, tasty, vegetable. Okay, fantastic. This is exactly the type of thing I wanted. So thanks very much. Yeah, so this is a photograph. It's not a photograph I took, actually. If you use Google, you'll find exactly the same photograph in the same way that I found this photograph. But it's a real photograph of a piece of food, a vegetable, and that vegetable is a special type of broccoli called a Romanesco broccoli. And I think it's quite beautiful, isn't it? I mean, if you've never seen one of these in the flesh, then you've missed out, but maybe you will in the future. But look at it. I mean, that's an actual broccoli. It's a real photograph of a real broccoli. It looks kind of interesting, I think. Okay, what's this? Sort of also looks a little edible, maybe. Cabbage. Yes, lots of answers of cabbage. It's a cabbage. It's a real photo, and you might think I'm using language in a strange way here. I keep on saying the phrase "real photo." It's a real photo of a real vegetable called a cabbage, or a red cabbage. This is like a cross section. So this was like a whole Romanesco broccoli, maybe with some of the leaves taken off. And this is like a slice through a red cabbage. And I also think it looks rather beautiful. And I hope everyone's had breakfast like me, because otherwise I'd be getting hungry looking at all these pictures. So real photo of a real broccoli, real photo of a real cabbage. Okay, this is a bit different. What's this? It's a fern. Yeah, Elaine was first to it there. It's a fern. I've even got, someone said it's Barnsley's fern. That's very advanced. That's correct, actually. It's a fern. It's supposed to be a fern, right? Real photo of real cabbage, real photo of real broccoli, real photo of real cabbage. This is not a photo, but everybody was convinced straight away that it was a fern, and a fern is a real thing. So I could have taken a real photo of a real fern, but actually I've got this sort of computer generated image of a fern. And it's not exactly clear how this image was generated, nor is it clear if this is representative of what the structure of a real fern would look like. But yet all of you identified it as a fern very quickly. So that's kind of interesting. So the thing I want to highlight as different about these three pictures is that this one is not a photo of a real thing. This is a computer generated image. These are real photos, computer generated image. Okay, what's this? A little harder this time. We're all warmed up now. No answers so far. Any guesses? Someone says, ooh, something about brains. And someone said, Maddie says a storm. So yeah, these are good answers. So I actually, I have no idea what this is. This is another picture I stole from Google Images. I have no idea what it is. But I like to think it's something like neurons interacting in the brain, or maybe electrical currents shown at a very, very small scale, or maybe electrical activity in weather shown at a very large scale. I don't know, but it looks something like that. And is it a real photo or is it a computer generated photo? I don't know. I suspect it's computer generated, but it's sometimes hard to tell. So I don't know what this is, but it's a nice picture, I thought. So lots of nice pictures. Okay, what about this? So again, it's not a real photo. It doesn't look like a real photo. It's a forest, a tree plantation, and someone's pointed out that it's not a real photo. That's true. An orchard. Yeah, I think it looks a bit like an orchard. So this is, again, it's a computer generated image, but let's look a little bit about what's going on with this picture. So I can see a sort of large tree in the bottom left corner. And then actually, if you look closely, you'll see that all subsequent trees are actually identical or scaled and maybe slightly squashed versions of the original tree. So what I've done is I've got a picture of a tree. This is just this single tree in the front left. And then I wanted to generate a picture of an orchard or a forest. And instead of having to draw all of the individual trees, what I did was I took the central tree, and then I wrote a very simple program which was going to reproduce this small tree at many different scales. And this is actually something which is used in real life in something called image compression. So if I want to have a picture which is complex and maybe would take a lot of effort to draw by hand or using a computer, but I recognize that the picture has lots of repetition. So I see the phrase repeating image of a tree from Donna, which is exactly this point I'm making. That it would save me a lot of time if I could just tell you about one of the trees and then write a recursive program which would then generate all the other pictures of the trees. And then I would get this complicated image just from this very simple image and then this simple set of instructions. And that's exactly what. So I actually produced this picture. I didn't. The first tree in the bottom left I didn't produce. I stole that from somewhere, but then I used it to produce the rest of the picture. So I didn't produce any of these pictures, but this one I did, and this one I did. So this is a similar idea. This time there's a central bird. This is a large silhouette of a bird, and then I've written a simple computer program to replicate the bird at smaller and smaller scales. So this is again an example of image compression. And this is supposed to represent like a flock of birds seen from above or maybe from below. So the birds are bigger if they're closer to me, and then if they're further away, sort of further up in the sky, then they're smaller. And they're flying in some sort of triangular formation. So this was generated in a very similar way to this forest here. And again, it's sort of related to the pictures we saw before, because like this one, it's a fern, but it's supposed to be, it's a computer generated picture, which is supposed to represent a real object, namely a fern. And it's done it in a fairly close way. Whereas this one and this one, they look less realistic simply because the main image which I took was a silhouette. And then also the program that I wrote to replicate this, the important image was much simpler. So in the end, the image I got was sort of less realistic looking, but much more computationally efficient to produce. It's not so clear where I'm going with this, right? This is just a Saturday morning ramble with lots of nice photos, but here's real broccoli, real cabbage, computer generated fern, mysterious lightning, tree produced to make a forest, bird reproduced to make a flock. What about this? What's this thing? Any ideas? Tablecloth design. I like that a lot. It looks like this would be a great tablecloth. So people have said spirals, spirals on spirals on spirals, a spiral of spirals. So lots of the word spiral. So last time I used this image in a talk, which was quite some time ago now, somebody said it's a snail. And I don't know about you, but I don't think this looks much like a snail. I mean, I know what they're talking about, but like I would be really scared if I saw a snail like this. I mean, this would be like a very advanced snail. And also, where is the head and where's the little antennae that the snails would normally have? So I think it's like an abstraction of a snail or something. But you know, when you look at a snail shell, there's this spiraling that goes on, and so maybe it's supposed to be imitating that slightly. So this is not supposed to be anything actually. I mean, of course it's a spiral of spirals, but it's not supposed to be representing any real life thing. So this was designed to represent a real flock of birds. This was designed to represent a real forest, but this is just designed to be a nice picture. But it's designed in the same way. So we have a sort of larger spiral that's then copied as we go around and spiral into the center. So it's a sort of similar principle to these guys, but it's not designed to be anything. But you might be forgiven for thinking that it was a spiral or a whirlpool or even a snail. Okay, the whole talk is not of this form, by the way. I will eventually do things which are not just showing random pictures, but I have a couple more after this, I think. Anyone know what this is? What does it look like? Maybe you don't know what it is, but what does it look like? Someone says this is cool, no idea. Yeah, I think it's cool. Abstract mountain with snow, cool. A mountain, looks like a triangle. Yeah, there's something triangular about it. Gavin says trench warfare. That's interesting. Not heard that before. Triangles. I mean, you can sort of see triangles, like triangles with different angles and of different sizes. You can see lots of triangles. So, Chris has said 1/p thingy. And actually, I know exactly what Chris means, and he's right. So this is a mathematical object, which I call the popcorn function. But it has many names. It's been called the stars over Babylon, and it's been called the raindrop function, and it's been called all sorts of other interesting things. But I call it the popcorn function. And actually, it's a mathematical object with a mathematical meaning, and the meaning is quite cute and quite simple to explain. So let me attempt to do that. So it's all about rational numbers. So rational numbers are, let's just talk about rational numbers between 0 and 1. So rational numbers between 0 and 1 are numbers which can be expressed as the quotient of two integers. So for example, 1/2, 1 divided by 2 is a rational number. 3 divided by 4, that's a rational number. 2 divided by 4 is also a rational number, but it's the same rational number as 1 divided by 2. So probably I should assume that all of my rational numbers are written in their lowest, in their simplest form, so with no common multiples on the top and the bottom. So hopefully everyone knows what I'm talking about. They're fractions of integers. So 2/3 is an example, 1/4 is an example, 2 divided by 19 is an example. I could go on. So this popcorn function is formed by considering rational numbers. So it's actually the graph of a function, and the input, so along the x-axis, along the bottom, is a rational number. So it takes a rational number between 0 and 1. Now, a rational number between 0 and 1 is of the form p divided by q, for p and q integers, right? I'm using abstract mathematical language, which is a bit cruel for a Saturday morning, but fractions are of the form 2 divided by 3, 3 divided by 4, for example. So a general rational number, a fraction, is of the form p divided by q. That's the input to the function. And the output to the function is 1 divided by q. So it takes a rational and sends it to 1 divided by the denominator of the fraction. So you've got this, this central dot, which is the highest point of the triangle. You can see the furthest dot, the most northerly dot on this diagram, that corresponds to the point 1/2. Because 1/2 of all the fractions that are between 0 and 1, 1/2 is the only one that has 2 as a denominator. So because 1 over the denominator is the output, 1/2 is the greatest output for this function. So it appears there at the top. And then the next highest points are corresponding to 1/3 and 2/3. 1/3 and 2/3 are the only rational numbers with 3 as the denominator between 0 and 1. And so this function sends both of those to 1 divided by 3, because 3 was the common denominator. So 1/3 and 2/3 both get sent to 1 divided by 3. And then the next line down, you can see only 2 dots. If you look carefully, the third line down from the top, we just have 2 dots, and they correspond to 1/4 and 3/4, because those are the only rational numbers between 0 and 1 with denominator 1/4. So 1/4 and 3/4 are both sent to 1/4. So anyway, you then continue this, and so as the denominator increases, you get many, many, many more fractions with that denominator. But then, so there are many more dots, but the output of the function is much smaller, because as the denominator increases, the denominator is q, 1/q decreases. And so I get this clustering along the x-axis, which corresponds to rationals with very high denominators. And so this function appears in all sorts of areas in mathematics. But if you draw it, it looks kind of nice. And that's the only reason I included it today. I'm not going to tell you any more about the mathematics of it, but I just included it because it's a nice picture. So Martina has asked, what's the name of the function again? It goes by many names. I call it the popcorn function, because I think of this as, like, imagine putting lots of popcorn seeds down on a pan. I've forgotten what you make popcorn out of. You put popcorn seeds on a pan, and then you heat it up, and then they start to pop and form popcorn. I guess it's corn that you put. The corn pops to make popcorn, and then they sort of all jump up, and they look a bit like this function. That's why it's called the popcorn function. Kernels. There we go. Thank you, Donna. But it goes by many names. So it goes by the stars over Babylon. It goes by the raindrop function. It goes, and some people call it Tomé's function. The mathematician, I'll put that in the chat. So there's a mathematician called Tomé who studied this. He was one of the first people to formally study this object. So sometimes it gets named after him. Okay, so anyway, it's just a nice picture. But I thought I would explain the mathematics of it, since the mathematics of it is quite cute. Okay, what's this? So lots of people identified it. It's the Mandelbrot set. It's the most famous fractal of all, perhaps. So, oops, I gave it away. This is a fractal. This is a very famous and very complicated to explain mathematical object called the Mandelbrot set. But if you've never heard of it before, I like to think of this as like, it looks like a crystal growth in a petri dish. So imagine, you know, these experiments you do in school where you put different chemicals into a petri dish and then you leave it overnight, and then like salt crystals start to form in the morning. I think this looks a little bit like that. So if you see these little dendrite things that are reaching out towards the corners of the screen, I think it looks a little bit like crystal growth in a petri dish, but maybe that's just me. But this is called the Mandelbrot set. This thing here, this is just a funky picture which I made. I wrote a computer program which produced this picture, and it's not supposed to look like anything real, but I guess it looks a little bit like a leaf, maybe. Also, maybe it looks like crystal growth. So anyway, these pictures, we've seen a lot of pictures now, right? I don't know which, maybe you have a favorite. The popcorn function seemed to get the most attention, but that's because I decided to dwell on the mathematics of it a bit more. So these objects were all fractals, and probably you all guessed that, because after all, this talk was supposed to be about fractals, and I started with about 10 pictures, and so if they weren't fractals, then it would be a little strange. So these are all fractals. But why? Why are they fractals? What is a fractal? Maybe you've heard of a fractal before, maybe you haven't, that's okay. But let's suppose you hadn't met fractal before, you've never heard the word fractal, and I just show you all these pictures and tell you they're all fractals. Well, what do you think a fractal is? So what properties, perhaps rather than asking what a fractal is, perhaps it's better to ask what properties did all of these objects have which made them fractal? Maybe that's a better question. So what do you think? So Donna's put repeating pattern, good. definitely repeating. There's some sort of repetition going on, like repetition on scale. Maybe it's easier to see here. There's a repetition, like the spiral is reproduced at smaller and smaller scales. Here that the tree is reproduced at smaller and smaller scales. So repeating patterns at different scales. They're all self-similar. These are fantastic. Repeating patterns of branching. Yeah, these are all wonderful answers. So here's a few things which I wrote down. I think they all share complexity, whatever that means. I mean, I think all of these pictures, like if we're used to like what shapes and what pictures do we normally see in mathematics, like we see things like circles and lines and squares and spheres and cubes, this sort of thing. These pictures which I showed you were all, I think, more complicated than those simple objects that come from like high school geometry. Self-similarity, yeah, so this was something touched on by several of you in the chat. Self-similarity refers to being made up of copies of oneself. If I suddenly take on the personality of one of these shapes. So if you notice, like this one, for example, it's made up of small copies of itself. So the whole picture is like this spiral of spirals, but each of the spiral is made up of lots of little spirals of spirals. So it's self-similar in the sense that the whole is made up of copies of itself. This is an important one, I think. I think they all look natural. And like, I'm cheating a little bit because some of the pictures were actually natural. I mean, I showed you a picture of a broccoli, which is natural, and a cabbage, which is natural. But I think, and some of the pictures, even though they were computer generated, were supposed to represent natural things. So like the fern or the forest, these were supposed to represent natural things. But I think all of them look natural. Like nature actually is more chaotic than sometimes we're led to believe. Like, you know, if you look outside your window and look at something growing, it's not growing in a straight line or in a circle. It's growing in some sort of irregular pattern that often has a repetitive nature. And this is basically due to the fact that biology writes with simple rules, simple recursive rules. Okay, so I think I have one more. So this is another important feature. This is these objects are not described by simple geometric objects. So you can imagine building a toy house made out of blocks. Like my 2-year-old son like has blocks and he builds stuff out of the blocks. Like those basic blocks are like circles, squares, triangles, cubes. And so you can build more complicated things out of these simple objects, but none of these fractals seem to be like that way. Like there was no squares used at all in this. Like no squares were harmed during the making of these fractal images. And I think that's also quite important. Here's another one which is was sort of hinted at by in the chat. So that they also seem to have detail at small scales. So like if I look at the picture, it looks quite complicated. But then also if I look at the picture like closer up, it still looks complicated. And this is also not the case for simple objects. Like imagine if I take a circle and I look at the circle, so the boundary of a circle, and I look at it very closely, then if I look at it really, really closely, all I see is a straight line, like a tangent to the circle at the point which I'm zooming in at. And then the straight line just looks like a straight line, no matter how close I look at it. But all of these pictures, the closer I look, the more complicated detail appears. So that's also something which is a property of fractals. Okay, so here is a simpler picture. Right, this is I've hinted at the simplicity of things like circles, squares, lines, triangles. So here is a triangle. I made it myself. I drew it using this advanced mathematics program called Paint. But I'm going to use, so this is not a fractal, right? This is just a triangle. But I'm going to use it to build a fractal. And this is actually going to show you how I made some of the other pictures. So this is a simpler mechanism because it'd be easy to explain, but this is sort of explains how some of these other pictures were made. So that's a triangle, right? What I'm going to do to it is a very simple operation, which I'm then going to repeat recursively And this is what makes it good for programming, because I can give it a simple rule and then repeat the rule and I get something interesting in the long run. So the simple rule is that I take this triangle and I imagine that it's a cake of some sort, which I like to do with most things. And I'm going to cut from this cake an inverted equilateral triangle of half the size out the middle. Looks like this. Oops. Looks like this. It's easier to explain with a picture than using phrases like inverted equilateral triangle. But this is an equilateral triangle. Let me suppose the base has length 1 meter, whatever you like. And then let me cut an inverted equilateral triangle of half the size out from the center and let me eat it. So there it is. That's what I get. I take the cake and I cut the middle out and I get now 3 triangles. I've cut the middle bit out and the 3 solid black triangles remain. So now I'm just going to run this, that's the rule, like you cut a triangle of half the size out from the center. Now I'm going to repeat this process on the other triangles. So start with a triangle, cut a triangle, an upside down triangle out from the middle. This leaves me with 3 triangles, which are very like the first one, but just scaled down. So now let me repeat this construction operation with each of these triangles that I have at this stage. So I do that and I get this. And then I'm going to just repeat. So I do it again, I do it again, and I do it infinitely many times, or as many times as the resolution on my computer will allow. And the picture that I get is this. So it's quite cool, I think. Like there's a very boring old triangle, nothing interesting about that. There's 3 boring old triangles, nothing really particularly interesting about that. There's 9 boring old triangles, nothing particularly interesting about that. But if I repeat it loads of times, then the picture gets really beautiful. And I get this this example of a fractal. And Elaine has hit the nail on the head in the chat by suggesting that this is called the Sierpinski Triangle, and that's absolutely true. This is named after a famous Polish mathematician called Sierpinski, and it's a famous example of a fractal known as the Sierpinski Triangle. Okay, so these fractals, which I'm talking about, they actually appear everywhere. So I mean, you can kind of already tell this because I've given examples from lots of different disciplines. I mean, I've given an example from the study of vegetables, whatever that's called, like broccoli, cabbage, etc. We've also seen applications in image compression, so producing complicated pictures by reproducing a simple picture many times using a computer program. That was the forest and the snail. We've seen some number theory. So from pure mathematics, that's the popcorn function. So we produced a fractal by considering rational numbers. We've seen the Mandelbrot set, but that reminded me of chemistry, so crystal growth in a petri dish. And then we've seen, the Sierpinski Triangle, which was, of course, another application in cutting up cakes. So fractals do appear all over science, mathematics, and even art, even not non-scientific fields, the fractals still appear. So here's some examples. So fractals are things which exhibit detail on small scales, which have some sort of self-similarity, which look natural, which look complicated, but yet are often generated by a simple underlying process. So, for example, if you're interested in finance, stock market fluctuations, so share prices can fluctuate dramatically over small and long timescales. The surface of a lung, or a human lung, if you're interested in medicine, a lung is designed to be able to absorb as much oxygen as possible. And so the way a lung works, it absorbs oxygen through little things on its surface. And so it's a 3-dimensional object, like you can picture it like a balloon, but the absorption happens through the boundary. And so in order to maximize the surface area, the surface of a lung actually has a fractal structure. And so it's like if it was just a perfect balloon, it wouldn't have the same absorption as something with a more complicated boundary. So finance, medicine. If you think about looking off into the distance, maybe if you're lucky enough to live in a mountainous region, then you see that the horizon has this sort of fractal behavior, natural, complex distribution of stars in the galaxy. So if you think about how so the surface of a lung, the fractal properties are happening on a very small scale. But if you look at the galaxy, like look at the Milky Way, then if you look at the distribution of the stars and planets, then that also has this sort of fractal appearance. So they're everywhere, right? Fractals are everywhere. They're all across science and nature. So let's get back to the discussion and the comparison with simple geometry. So the geometric objects that we study in school: circles, lines, triangles, spheres, cubes, this sort of thing. Where are they in the real world? So this is, I want to go back to the chat again. I've been talking too long without appealing to the chat. So where are circles, lines, triangles in the real world? So give me an example. So I see, so two people have written architecture. That's must be, what a coincidence. So in architecture, man-made things, right? When we make things ourselves, they tend to follow more regular geometric patterns. So when we make a house, we tend to make it out of straight lines. Like look around the room you're in right now. Probably the ceiling has, the boundary between the wall and the ceiling is probably like a straight line, right? Well, actually, there's nothing straight about that line. It looks like from where you're sitting, look up at your ceiling right now and focus on something that you think is a straight line. It looks straight, but actually it's not straight. There's nothing straight about it. If you look closely, if you look really closely at that line, you'll see all sorts of irregularities forming. You'll see little bits where the paint is flecked off, or where there's some dirt in the corner, or just the house is just naturally a bit curved. Like my floor in my house is not particularly level. So you'll find that it's not straight at all. And even things which are built with great engineering precision, like bridges or cars or trains or planes, they're designed like following this ideal of being straight lines, but actually there's nothing straight about them at all. If you look closely, even if you find the straightest line, like look at in your pencil case. Do people still have pencil cases? In my day, I had a pencil case when I went to school, and in that pencil case, I had a ruler. And if a ruler, of course, must be straight, right? I mean, that's the whole point of a ruler, is that it's straight. But actually, if you look closely at the ruler, really closely, even through a magnifying glass or something, if it's a really good ruler, you'll see that it's extremely irregular. So actually, there are no straight lines or circles or triangles or squares in the world, in the universe, anywhere. That's a pretty controversial thing I've just said there. And I'm very happy for people to try to argue to the contrary. So if anybody wants to come up with an example, I've just claimed something crazy, right? I've just said squares, circles, lines do not exist. They do not exist. You can't find them. Does anyone want to prove me wrong? So we've got the word Bermuda. That's interesting. So the Bermuda Triangle is supposed to be this like place where ships go to disappear. I mean, it's not. If you look, I mean, it's like waves and everything. I mean, it's very irregular. Actually, it's probably not completely well defined either. So people say things like laser beams. Like if you shine a laser beam, surely that's shining in a perfectly straight line. But no, it's not. It's what is a laser beam other than little particles of light? I mean, I'm no physicist, but little particles of light being cascaded in a very accurate way at a wall. But actually, if you looked very closely at that laser beam, you'd find that it was completely chaotic all over the place. In fact, it might look actually more like that one of those first pictures that I showed. The one that I didn't know what it was. It was the neurons firing and the lightning, like that. Maybe that's what it looks like if you look really closely at a laser beam. So it's just, I mean, I could argue this point all day, and it's great fun to do so. But unfortunately, there's not enough time, I don't think, to really dedicate any more time to it. But I love getting people to try to come up with examples of straight lines in the world, but because they just don't exist. you'll always find that if you look closely, you find irregularity. If you look at the edge of your table close enough, you'll find irregularities. And even if it's made with some incredible engineering precision, if you look close enough, eventually it just becomes like molecules and atoms floating around. There's nothing straight about it, okay? So what, it's kind of strange. In school, the first thing we do in geometry is study circles, lines, triangles, squares, but they don't exist. There are none of them. It's not like there's not many of them. There are actually none. There are no circles in the universe. So why would we study them? But of course, the answer is that they exist in the abstract. So Donna put in the mind, which is actually, I think, a great comment, that the concept of a line exists. The concept of a circle exists. And studying the concept in abstraction helps us greatly when we then come to be engineers or architects. So this is the same idea. So what's the point of this attack, this unwarranted attack on the straight line, is that I want to make the point that this is how we study fractals too. So not only do fractals appear much more easily in real life, like real life actually is fractal. We have fractals everywhere. But in order to study them, we have to take them from an abstract point of view. So that was like this Sierpinski Triangle thing, which I built. Here's a picture of it. It's an abstract fractal. Like this is not really, like here's a triangle, but it's not really a triangle because it's made up of pixels. And if you look really closely, the resolution will break down and you'll see that the edge is pixelated and it's actually nothing like a triangle. But I used it to build this fractal. It's an abstract fractal. And so now I want to study mathematical problems or mathematical questions about these abstract fractals in the same way that I studied abstract properties of lines, circles, squares. So the whole point of the geometry lessons in high school, when you meet circles, lines, squares for the first time, is because you're studying them in the abstract, and the knowledge you can get from studying things in the abstract feeds very effectively into real life. And that's the same idea with fractals. Okay, so where was I? Oops. So, okay, here, and now for the last 10 minutes, I'm going to talk about a real research question. So I'm going to take you now right to where my research and the research of others actually sits in terms of these fractal objects. So I want to ask geometric questions about fractals. And one of my favorite geometric questions to ask about a fractal is about its dimension. So on the screen now, you can see a line. I by mistake showed a few clicks ahead, so possibly I spoiled the surprise. But a line is a geometric object, and it has a dimension. So does anyone want to suggest what the dimension of a line should be? Just stick it in the chat. We have someone suggested 2, and then we have 2 people suggesting 1. 1D, yes. I think 1 is probably a more conventional answer. So a line is a one-dimensional object, right? So there it is. The line has one dimension. Here's another geometric object, a square. Of course, it's not really a square because squares don't exist, but it's a computer representation of the abstract concept of a square. But for the time being, let me just call it a square. So what's the dimension of a square? 2. So lots of people have said 2. Good. A square is 2-dimensional. And here's a cube. Okay, it's not really a cube. In fact, it's not even really a representation of a cube because it's printed on 2-dimensional paper. So this is like an artifact of how mathematics is communicated in this 3-dimensional world we live in. That I'm showing you things on a 2-dimensional screen. And so it's easy to show a 1-dimensional line and a 2-dimensional square on a 2-dimensional screen. But drawing a cube on a screen is difficult. So actually this is a 2-dimensional projection of a cube. But it's not really a cube because cubes don't exist. But for the purposes of this discussion, let me call it a cube. So what's the dimension of a cube? 3, good. So the line is 1-dimensional. The square is 2-dimensional. The cube is 3-dimensional. Now, basically everybody who answered got it right. So why did you get it right? And on what basis did you assign dimension 1, 2, and 3 to these objects? Does anyone want to comment on that? What makes a line one-dimensional, a square two-dimensional, and a cube three-dimensional? So I think it has something that maybe people are frantically typing at the moment, but let me just skip ahead. Yeah, length, breadth, height, right? A few people have mentioned length, breadth, height. In order to describe your position on a cube, you need 3 bits of information: the length, the breadth, the height. Whereas a square, you just need 2, length and breadth, and a line, you just need 1, length. So it's something to do with degrees of freedom. But how do I define the dimension of a fractal? Because a fractal is a much more complicated object. Like the lines, squares, and cubes are almost by definition 1, 2, and 3 dimensional. So how do I define the dimension of a fractal? So what does dimension even mean? So imagine like the Sierpinski Triangle. Let me find it again. Like this is now what I want to do for the next 7 minutes. I want to try to decide what the dimension of the Sierpinski Triangle should be. And like our old notion of dimension comes from degrees of freedom, but that's just not going to work here. Like it's too complicated. So we need to come up with a more robust definition of dimension. And here is one. Now this is now going to get, I mean, I think we've had lots of friendly pictures and lots of philosophizing. So I'm going to ramp up the mathematical level ever so slightly in this last few minutes. So consider this proposal. I want you to take, so we have an object, and I want to determine this object's dimension. So in order to do that, I'm going to consider a very, very small length scale, which I'm going to call R. So maybe the object that I'm interested in is like 1 meter in diameter. And so then the scale R is like much less than 1 meter. Like maybe it's 1 millimeter or something, like much, much smaller than the diameter of the object. Now what I'm going to do is I'm going to take lots of little squares of side length R, and then I'm going to try to place them on the picture of the object that I'm trying to characterize. And I'm going to count how many of these objects do I need to completely conceal the picture. And this will be clearer in a minute. So I want to call, so that this gives me a number, right? So given an object and a scale, which I'm denoting by R, I want to count how many little squares of side length R do I need to cover the original object. This gives me a number, like an integer, whole number, and I'm going to call this number capital N of R. So it depends on R, of course. So as little r decreases, capital N of R should increase, right? If I take smaller little squares, I'm going to need more of them to cover the object that I was interested in, okay? Now, the question is, and the question which is going to determine what dimension means, is that I want to understand how this number grows. So let's consider some very simple objects. Unfortunately, we have some simple objects in our armory by now. So imagine a line, right? I have a line which is 1 meter long, and I give you lots of little lines which are only R long, and R is very small. Then how many of these little lines will I need to cover the long line? Well, the answer is 1 divided by R, roughly, right? Because I take the length of the total thing, which is 1, and I divide it by the length of the little thing which I'm using to cover it. And this gives me 1 divided by R, and 1 divided by R is R to the minus 1. So the covering number for a line should be roughly R to the minus 1, okay? For a square, so now imagine a square. I want to cover the square, 1 by 1 square, with R by R squares. So it takes 1 over R to cover the base, but then I also have to cover the height. So that's another 1 over R. So I get 1 over R times 1 over R, which is R to the minus 2. Similarly for a cube, the covering number is R to the minus 3. Now what you should notice is that the dimension of the object has appeared. So the line was 1 dimensional. So the number 1 appeared as the exponent. the square was 2-dimensional, so number 2 appeared in the exponent. The cube was 3-dimensional, so the number 3 appeared. So maybe in general, this covering number should behave like r to the minus whatever the dimension is. And in fact, this can almost be taken to be a definition of dimension. And the advantage of this definition is that it applies to any object. It doesn't depend on some notion of degrees of freedom or length, base, height, etc. This applies to any object. I just need to take an object, work out how to cover it at small scales, and then observe this growth, and this will tell me what the dimension is. So let me just finish by computing the dimension of the Sierpinski triangle really quickly. So I need to cover the Sierpinski triangle with little squares of side length r. So let's suppose, to make the calculation easy, let's suppose little r was 1/2. So here the Sierpinski triangle has a base length 1, and this is a square of side length 1/2. So how many little squares will it take to cover the Sierpinski triangle if their size is 1/2 by 1/2? Well, the answer is, I can place one there, I can place one there, I can place one there. The answer is 3. Let's try again. So if little r is 1/4, then how many little r squares is it going to take to cover the Sierpinski triangle? The answer is 9. Now, if I'm making my scale smaller and smaller, because I have to understand it for small scales. So if my little scale is 1/8, which is can be rewritten as 2 to the minus 3, then the number of squares required to cover the Sierpinski triangle is 27, which is 3 cubed. So in general, if I assume that my little length scale has size 2 to the minus k, then it was easy to estimate the covering number, and the answer was 3 to the k. Right, I've generalized here, but you can see the first 3 examples, k equals 1, 2, 3, and then we can extrapolate. So what I need to do is express 3 to the k as the little scale r, which in this case is 2 to the minus k, to some power. So actually, it turns out that 3 to the k is roughly 2 to the 1.58 k. So the covering number, when r is very small, should be roughly r to the minus 1.58. Or if you've met logarithms, which I realize some of you towards the senior end of high school may have met, but most of you probably haven't. So if you haven't met logarithms, just forget this remark. But if you've met logarithms, then you can solve this equation explicitly, and you'll find that the exponent is log to the base 2 of 3. And so the dimension of the Sierpinski triangle is log to the base 2 of 3, which is roughly 1.5849625. So this fractal object, this Sierpinski triangle, had dimension intermediate between the line and the square. And in fact, the dimension can be most appropriately characterized as around about 1.58. So anyway, that's me stopped just on time, imagine that. Thanks very much for your participation. That was really great. I was really worried about how much interaction we were going to get from not being in person, but I really appreciate how keen everyone was to interact with me via the chat. So thanks very much. I'll stop there.
Brilliant. Thank you very much, John.